Okay. Hi, everyone. Welcome to the class. So I'll start a lecture on whiteboard using pen and paper. I will first have to focus it. So, okay. So look, last time, this is, by the way, the same content as is in the slides. And I believe this is starting chapter 3 in Katzländer. I don't have the textbook in front of me, but it's farewell to perfect secrecy and starting the so-called computational notion of security of encryption. Okay, so last time we pointed out that if encryption is perfectly secure, then the key space has to be at least as big as the message space. And one consequence of this is that keys have to be as long as messages. And, you know, if you think that, oh, okay, you know, your keys are 100-bit long, your messages are 100-bit long, but I'm going to send many of messages like this. And perfect security holds only if you use, hold on a second. Sorry, I have to take a tiny break. Sorry. Okay. I have to take like a 30-second break. Hold on a second. Okay, I apologize. Sorry. Had to answer some question here. Okay, sorry about that. If I knew anything about like video editing, I would cut it out of the video, but sadly I don't. Okay. So holds only if you use the encryption, the key once, right? So, okay. So this is pretty bad. What do we do, right? Because I want to be able to encrypt, you know, several megabytes of traffic. I need a several megabyte long key, etc. So this is not good. So that's where the notion of computational security of encryption that's where it takes its beginning. The idea is how to restrict this notion of perfect security, and so that it's still meaningful, but it allows us to go over this bound. So the keys can be 100 bits, but we can encrypt megabytes and gigabytes with them. Okay, so remember the setting of perfect security. What was the experiment? Alice had some message M that she wanted to send, right? She chose a key at random from the key space. And what she showed to the adversary, because she really wanted to show it to Bob, right? But the adversary is on the wire, so he gets to hear everything that she communicates, is C, which is an encryption under this random key K of message M. And we wanted to say that adversary learns nothing about M. Okay, in what sense perfect secrecy did it? Because it considered really two messages, M, let's call them M0, and let's call the other message M1. And you got, in the second experiment, the question is basically, is it M0 or is it M1? This is the question that adversary has. So in this case, he gets an encryption of M0. And in this case, he gets an encryption of M1. Okay, and how does perfect secrecy imply this? Because perfect secrecy says that this random variable and this random variable are identical. So perfect secrecy implies, that's what we argued last time, that C, which is an encryption of M0, and if you think of this as a random variable given a random choice of a key, is an identical random variable to C that comes out as an encryption of M1. Again, this is a random variable imposed by random choice of the key. So this means that these two, the left and right random variables are identical. In other words, distributed in the same way. So, for example, for a case of one-time pad, no matter what M0 is, this is a random n-bit string, and no matter what M1 is, it is also a completely uniform n-bit string. So this holds for all M0 and M1 in the cipher, in the message space. And therefore, basically adversary cannot tell which case he is in, right? Whether he's in the world where Alice sent M0 or in the world where Alice sent M1, he cannot tell, because in both worlds he gets the same random variable. In the case of one-time pad, a uniform n-bit string here and a uniform n-bit string here. So there is no way for him to tell. Now, that is, unfortunately, has this bound, right? So how can we relax this? There's two ideas. What if we don't care about all adversaries, but only adversaries with polynomial time computing power.
Sorry, Professor.
Mm-hmm.
What do you mean when you say the two C random variables are equivalent? Or is that like saying the probability of getting that ciphertext as the adversary is the same, so we can't distinguish
Precisely.
which message it is? Okay.
Yes, it's the same random variable, meaning that whatever value this random variable attains, whatever. So for every value, the probability that this guy gets that value is exactly the same as the probability that this guy gets this value.
Okay.
In the case of one-time pad, every bit string comes out with exactly the same probability, which is 1 into to the n, where n is the length of these bit strings.
Okay, thank you.
Okay, so in other polynomial time, we were going to abbreviate it by calling it efficient. Okay, so I mean, it's the whole thing. It's just abbreviated as an efficient adversary. So in other words, okay, what if the cipher had the property that an attacker, if attacker has performs exponentially many operations, exponential in what? In the length of inputs. So say the length of the ciphertext. But assume at first that everything has roughly the same length. So keys, messages, ciphertext are all n-bit, and or some constant away from n-bit. Okay, so this input this guy gets is n-bit. Let's say that in space in 2 to the that he can basically with a brute force attack. Let's say keys are n-bit long. So a brute force attack means that he searches through all possible 2 to the n keys and tries to decrypt. Maybe that attack succeeds. It actually does not succeed against one-time pad, right? I can search through all possible n-bit strings and decrypt the ciphertext under them. And precisely for every key, I'm gonna get a different message, and they're all equally likely, just like this thing. For every key, I'm going to get a different message. So even the brute force attack does not work. But let's say that you have a cipher where the brute force attack did work. So if I search through all the possible keys, I could confirm that that's the one that somebody uses. If that was the only attack, well, maybe that's fine, because I just make the key say 100-bit long, and if the only attack requires 2 to the n, which is 2 to the 100 operations, well, maybe that's okay, right? Because 2 to the 100 is more than a feasible computation. And if I'm, if I think that 2 to the 100 is feasible, okay, so then just take this key to be 200 bits, okay? And now the brute force attack has 2 to the 200 complexity. So that is one thing that should satisfy us, right? Because if we knew that the only way to attack is to expand exponential computation, and the length of these things is high enough so that the exponent in that is a really large number, we should sleep safely, soundly, right? Because we should feel safe. Another, okay. So, unfortunately, if I limit this attacker to just polynomial time, then and I still require, well, so okay, so how about we don't require that the input of the attacker are distributed identically? Instead, we ask that the attacker outputs something. And I'm just going to say that this output I'm going to call it a bit, and for reasons that will not be apparent at first, I'll call this bit B prime. Okay, and here too, right? Because well, adversary is just an algorithm. It gets a ciphertext and it computes a bit. What if I said that it's the outputs that have to be identically distributed, not the inputs? In other words, what if I said, can I ask that encryption is computationally secure if for all efficient attackers, I'm going to just abbreviate them adversary, the distribution of outputs of the attacker on inputs, which is encryption of M0 for K random, is identical to the distribution of outputs of the same attacker, but now I'm giving him encryption of M1. Sorry, the key is random. Okay, so here you have outputs of an attacker who is fed with an encryption of M0, and here you have an output of an attacker who is fed with encryption of M1. In other words, I'm comparing this random variable to this one. And okay, what if this held? So an encryption was such that every efficient attacker and every two messages, so again, all M0 and for all M0 and M1 in the message space, has the following property, that if you look at the outputs of an attacker who gets this encryption, random encryption of M0, and you compare them to the outputs of the same attacker who is fed with as an input a random encryption of M1. And it helps that for every attacker, efficient attacker, and every M0 and M1, these outputs in the one case are identical to the outputs in the other case. And these two are random variables again, right? So with some probability, well, with that string, his output could be, one string with some probability or another string with another probability, etc., depending on the input. Without loss of generality, we can restrict this output to be a bit. And the interpretation of this bit, it's the best to think of it as a judgment that this attacker adversary algorithm makes about whether his input is an encryption of M0 or an encryption of M1. So let's just interpret this bit as when adversary outputs 1, first of all, it's a bit. And the meaning of this is like this. If this bit is 0, then this algorithm decided that this ciphertext is more likely to be an encryption of M0 than of M1. And vice versa. If this output is 1, then this means the judgment of this algorithm that the input is actually more likely to be formed like this than like that. Okay, so we can just rewrite this whole thing, therefore. Okay, we can, if without loss of generality, output B prime can be a bit. in which case then this definition this simplifies, because there is only two values of this B prime can have, the 0 and the 1, to the following. E is computationally secure if for all efficient adversaries, efficient algorithms ADV, which is my abbreviation for adversary, and for all messages M0 and M1 in the message space, it holds that probability that B prime is 1 for B prime output by adversary on input encryption of M0, and this probability goes over random key. And of course, randomness of encryption and possibly randomness of adversary, and randomness of encryption and adversary, that this probability is the same as the probability that B prime is 1 in the other case. So B prime is output by adversary on input encryption of M1. Where this also goes over random choice of the key and randomness of E and adversary. Okay. So it's, what does this say? It says that no matter what efficient algorithm you take, for any two messages in the message space, if you look at the probability that this attack algorithm, given an encryption of M0, actually thinks that it's an encryption of M1 because he outputs 1. And if you compare this probability to the probability that the same algorithm thinks that it deals with an encryption of M1, given that actually he has an encryption of M1. If his probability of thinking it's M1 in the correct case is the same as thinking that it's M1 in the wrong case, therefore, whether he thinks that he got an encryption of M1 or not is independent of whether he actually sees an encryption of M1 or he sees an encryption of some other message. So again, you basically got the same effect as with perfect secrecy, but rather than thinking of the cipher itself as this random variable, you are putting one more layer in between a cipher and a sort of, and the semantics of it. You say, I'm not going to look at the cipher itself. I'm going to look at the output of some efficient attack algorithm that tries to make a judgment about whether it's an M1 or not that is encrypted, given the ciphertext is the only input. And this also does not, I didn't say this here, but adversary should also, for fairness, be given these messages M0 and M1 as input. So it should be stuck in there. Not only his inputs include not only the cipher, but these two messages as well. So he sees, okay, here are the two messages that Alice could be sending, and here is the ciphertext. And given these three things, I'm making a judgment whether I think it's more likely to be this or that, and the judgment is identical, apparently, whether or not this cipher is an encryption of M0 or an encryption of M1. So by the same argument as what that was justifying why asking for perfect secrecy makes sense, why it makes sense to ask that these two are identically distributed. Well, if we agree that all attacks, it's enough to model them as efficient algorithms, and if there exist exponential time algorithms, we don't care, because we can make input long enough so that this exponential time is really infeasible. Then we should be satisfied, I would argue. Okay. But this is not enough. Why? Okay, now I don't know whether I should add this strong statement, but yes. If keys are shorter than messages, then this cannot be achieved. Then, you know, this property, the star property cannot be achieved. And I'm thinking whether I should make this as a homework exercise, but the idea is this. If it's actually, the intuition is very simple. If keys are as long as messages, then an encryption can have this kind of very nice in the way property that for every ciphertext can be decrypted into arbitrary message. That for every ciphertext message pair, there always exists a key that explains this ciphertext as an encryption of that message. But if space of keys is smaller, then now it will no longer be true. There will be some ciphertext and two messages such that the ciphertext can be explained as an encryption of the left message of message M0, but there is no key that can encrypt M1 into C. Just because the cardinality of the space is smaller, so you will be able, you know, take C and decrypt it with all the keys. So take M0, encrypt it using key K. Okay, take that function, right? The encryption function on M0. And now try to decrypt it over all keys in the key space. So you have, you know, the set of possible decryptions, right? But this set has only K elements. So it's a strict subset of M. So there are some messages here, and just call any of them M1. This ciphertext cannot be an encryption of M1. There exists no key which makes this ciphertext decrypt into M1 under this condition. Okay, what does this imply? This means that if there is attacker sees this message as possible, and a ciphertext, then he can attack like this. Okay, I say going through all possible keys and trying to decrypt and seeing that there is a key that will move back, right? This key that will move, sorry, so M0 is in this set. Actually, M0 is in here somewhere. Well, that key will be found. But none of the keys decrypt as M1, so that's an exponential time algorithm that will decide this bit perfectly, and right? But that's an exponential time algorithm. It's not efficient. Okay, but here is a trivial efficient algorithm. It just takes only test a polynomial fraction of these. And then, okay, let's say that he tests, you know, n of these, or even, you know what, let's take one key. So with probability 1 over the size of the keys, he will get M0. So A thinks M0 is encrypted with probability 1 over 2 to the n, because so the attack is, given the ciphertext, given these two messages, I'm just going to pick a random key and try to see if I'm lucky. If C decrypted under this random key is M0 or M1. With 1 in the space of keys, I will find a key that decrypts to M0, and therefore I will think it's M0. But A thinks, this attacker will think that the decryption is M1 with probability 0. Because no matter, you know, there is no chance that you pick a key that decrypts here. And these two are not equal. So the probability that he thinks it's 1 in this case is 0. And in this case, it's 1 into 2 over n, right? So it's banked. Oh, I mean, it just can, you know, it's not achieved. And this basically, this argument requires nothing about the encryption. You know, I didn't use any special properties of encryption. It just required this, and it already violated this property.
Professor?
Uh-huh.
Yeah, so I understood the point where you said that because when you decrypt the ciphertext, you will only have k elements, but I sort of didn't get your the explanation of A thinks M0 with probability and A thinks M0
Well,
with probability 0.
Okay, so pick M0, M1, and C.
Sorry, what was that?
No, so, you know, it will actually work for any M0 and M1. Pick any M0 and M1. Okay, so this attack is supposed to work for, you know, there is supposed to be for all, right? So, so take any M0 and M1. And okay, so it's a little more complicated than this, because what I'm saying now is might not work for really every M0 and M1, but just for enough fraction of them.
Oh no, I was just trying to understand what he meant by A thinks M1 with probability 0 and A thinks M0 with probability. That, I think that part I sort of.
So so by this I mean A outputs. So when I say A thinks M0, that's the same as to say A outputs B prime equals 0. And A thinks M1. What I meant is that A outputs this B prime S1.
Oh yeah,
right?
but why is that exactly? If you could
okay, now what does algorithm A do? So A on input M0, M1, and C acts as follows. Pick a random key k in the key space, output B prime 0 if a decryption under the key k of C is M0, output B prime 1 if decryption KC is M1. And I don't really care what you do otherwise, output nothing otherwise. Okay, so just output like a rejection symbol. I refuse to answer. So choosing this bit at random also works. And in fact, if he just always just blindly answered either 0 or 1 in a fixed way, that would also work. But this is the easiest, I think, scenario. So he picks a random key, and if that key happens to decrypt the ciphertext he gets as M0, then he outputs 0, meaning he thinks M0 is encrypted in C. If it happens that this random key decrypts C as M1, he outputs 1, meaning he thinks that M1 is encrypted in C. And if he's not lucky, then he outputs nothing. And if M0 and M1 are set like this, then just because there is not enough keys in the message space, there's always a message that is outside of all possible decryptions of C. Because the possible decryptions of C are just this many, right? As many as keys, right?
Yeah.
So on the encryption of the right message, he will basically never think that it's the wrong one, because the wrong one is outside of that space, of that subspace of messages.
I see. So,
Okay, but
yeah,
it's I'm a little bit fudging here because it doesn't quite work. Like it's not obvious how he should choose these messages to really assure this property. So for some cipher, it's going to be easier. We can see this, you know, in just next week, that it cannot be secure against this, and a general cipher is like a little more. It actually will work for random messages chosen. But the argument that random messages have to have this setup is okay, a little more involved.
I see. Yep.
Or that they are like this with high enough probability. Okay, because you know, basically with some probability, this guy is in that space, right?
Yeah.
Okay.
Yeah.
Okay,
Professor,
so yeah.
just to follow up on that, so would A actually have to, he would have to actually cycle through every key to confirm that probability, right?
No, he's super efficient, right? So at first you think, okay, I want like an you know, this is a brute force attack, it's exponential, he has to search through all keys. But no, actually a very efficient algorithm that just has a single key and doesn't care anything about others. Already that algorithm has a non-zero difference with which it outputs this bit in this case and this bit in this case. They have this type of probability difference. It's a tiny probability difference, right? If you think n is 100, then this probability, is pretty minuscule. But it's not zero. They're not identical as this equation asks for.
Sure, but wouldn't the adversary, like, doesn't he technically, like, before he knows, I understand that the probability would be 0, but what if he chose every other 2 to the n-1 keys that were not for that message, right? Doesn't the algorithm have to,
So okay, what I want is to get an efficient attacker, right? Because in order to this asks, I know that there is an inefficient one that can go through all 2 to the n keys.
Okay,
and
so
that's
by
brute force decrypt. But I don't care about that kind of attack because I restrict myself to efficient ones.
Okay, so we're saying it's efficient, so he can basically pick the right key just to determine the probability.
No, I wouldn't say it like that. He can pick the right key. No, he can pick a random key and hope that it is right. Right?
Okay.
He doesn't like pick, okay. The algorithm picks a random key. And, here's the algorithm, right? He picks a random key outputs this in this case, outputs that in this case, and outputs nothing in the other cases. And now let's analyze the probability with which it outputs these things. And it's simple, right? It will, if the encryption is of M0, then he will output 0 with probability this. And if the encryption is of M1, then he will output with probability 0, right? Because or he will output 1 with probability. Sorry. So hold on, I got myself confused here. Oh, you know what? Yes, I did. I'm sorry. I did sort of. I'm saying the wrong thing here, and no wonder you were confused. I'm sorry about this. Okay. Okay. So, oh, fine. Let's. Sorry about this. Let's do it in a better way. So let's say that there is a key that encrypts that M0 is in the space of that M0 belongs that C is an encryption of M0 for some key K. And M1 is chosen so that for all keys K prime, decryption of C is not equal to M. Okay, so these are all possible decryptions of C. And the message space is larger, so there is something outside of it. Okay, so let's say that I chose M0 and M1 to for this to be maybe I should say if C is an encryption of KM0, then M1 satisfies this property. Okay. So in order to, okay. So, so here I have scenarios: message encrypted in C, and here I have bit B prime output by attacker, and the attacker is this algorithm. Okay, sorry, I'm denoting him A, but and here I'm denoting him adv, but it's the same algorithm. Okay. So let's say that C is an encryption of M0. Then now the probability, so B prime is 0. In other words, this algorithm is going to output 0 with probability 1 into the n, right? If I assume that keys have 2 to the n elements, so keys are n-bit strings, right? Because this attacker, he sees the ciphertext, his code is here, so it is there exists, so it's at least this probability, but maybe there is some other key that if he decrypts the C under that other key, he also gets M0. But at least there is one key because C really does encrypt M0. So C is an encryption of M0 under some key. So that key can be, is going to be found here with the probability 1 into 2dn. Maybe there is some other key that also decrypts C into M0. That's why I write more, possibly more. Now, is there a probability that, what's the probability that B prime is output by 1? Well, that happens with probability 0. Okay, because by this design, none of the keys decrypt C into M1. So he will never get into this line. This test will always fail, no matter what key he chose. So the probability that this test succeeds is 0. Whereas the probability that this test succeeds is at least 1 into the n, when the probability goes over the random key choices the attacker makes. Okay, and the output is with overwhelming probability. Overwhelming probability, but I don't care. I'm only care about is there a difference between this and this one? Now I have to compare it to what happens if the encryption is M1, right? So actually, I don't know what will happen.
And that the B prime equals 1, wasn't that the probability for M1 since it's outside of the key space?
No, but so in this case, I have to consider, okay, what does attacker do when he gets an encryption of M0, and what does he do when he gets an encryption of M1?
Oh, okay.
Okay, so let's consider a case where C is an encryption of M1. And the probability that B prime is 1 is this attack, right, will clearly do this, right? Because if C is an encryption of M1, then look at this code. This code, given this C, right, it picks a random key and it outputs 1 if this line is satisfied. Where, well, there is this probability that the key chosen here is the correct key that was used in this encryption. So if C is an encryption of M1, there is some key that encrypts M1 into C and decrypts C into M1. So if this random choice of a key happens to pick that one, this line will be executed. So attacker will output 1. And what's the probability that this happens? Well, it's at least for that one key. There's perhaps more. And now this is the lines you should focus on, right? This one and this one. Because this means that the probability that B prime is 1 if B prime is output by attacker on encryption of M0 on for a random key, this probability is 0, and it's not equal to the probability that B prime is 1 given that B prime is output by the attacker on encryption of M1, right? They are not the same because this is 0 and this is at least 1 into the dn. Okay, so now now should be clear.
So if the messages are different, isn't that saying that the message now has a bearing on the output of the adversary? Because I thought M1 was outside of the realm of possible ciphertext, right?
No, plain
From that
text. Plain text.
Or
No.
wait.
They're made like this. M1 it's impossible to decrypt if C is an encryption of M0, then it's impossible to decrypt C as M1. So there exists no key that decrypts C into M1 because the number of keys is smaller than a message space.
Yeah, I understand that. So then in the second entry of the table for M1, how does B prime equal 1 with probability of
Because
greater than
that's the case where C is an encryption of M1.
Oh, okay. So I was sorry, I was looking at the diagram while you're right. Okay, so it's if the diagram was flipped, right? If M1
right. So
was
this is,
okay.
the table is compares two things. What's encrypted in C and what's the probability that attacker given that ciphertext outputs bit B prime equals 0 and bit B prime equal 1. Right? Because that's what this table has to, that's what the definition wants to compare. Let's look at the probability that he outputs 1 given an encryption of M0. So we are here. So we are considering this probability. And comparing it to the probability that he outputs 1 given an encryption of M1, which is here, which is this probability.
Okay.
Okay. But if I try to, generalize this attack, this attack, picking some random keys and just trying my luck. Well, if the size of keys is exponential, then even if I choose some polynomially sized subset, it's always just very tiny, right? Compared to the exponential size of the whole key space. So perhaps I am able to take n keys. Perhaps I can take n square, n cube, but whatever this, if attacker tests, say, n, polynomial of n keys in the key space, the advantage of attacker grows only to that polynomial divided by 2 to the n. Okay, because basically, so he tries his luck rather than abandon, here, he just recurses and he says, okay, let me try another key. Test if C decrypts to M0 on that one. Test if C decrypts to M1 on that one. No, let me try another one. And he does it polynomially many times, right? So you can think of this as any polynomial you like, right? Like n to the 5th, okay, n to the 4th, whatever. And intuitively, basically, this means that he succeeds. He will succeed, right? But with probability that is, he only searches through some small subspace still, because whatever polynomial of n, it basically pales in comparison with 2 to the n, right? So you know that from basic, from earlier classes, that as n grows, this gets smaller and smaller, and it will attain arbitrarily small value quite quickly. Yes, so whatever your threshold of resistance to attacker is, let's say 2 to the minus 100, whatever this polynomial is, it's going to be very fast for n to be such that this thing is smaller than 2 to the minus 100. no matter how big this polynomial is, as long as it is polynomial, then n will be just a little bit larger than 100, but not much. Okay, so this actually is the real definition, because if you say, okay, look, these type of attacks, yeah, they can create, they violate this property. So they show that it's impossible to achieve that a judgment of even efficient attacker, given a ciphertext, given an encryption of M0, and the judgment of the same efficient attacker given an encryption of M1, that these two judgments will be identically distributed. So they will be, let's say, one with exact same probability. That's impossible. Here is a counterexample. They're not one with exact same probability. There is a 0, and there is a tiny thing, but it's not 0. And this, can be extended like that. Okay, this type of attacks, this will remain 0, and this will grow to some polynomial over to the n. But even that is not really much. So here is how we stated, and the notion that actually is possible to achieve, under some assumptions, because without assumptions, basically, we cannot have efficient crypto systems without some computational assumptions. So basically, if all problems that we have trivial algorithms that require exponential time, if there is always some polynomial times algorithms that solves them, then cryptography is impossible at all. But maybe that is a strong statement. So maybe, but yeah, no, I don't think that's a strong statement. Okay. So, so the last time I tried, right, I made this, okay. So here is the second limitation that computational security is going to introduce. What if we don't care about tiny adversarial advantages? Advantages in what? In distinguishing encryptions of M0 from encryptions of M1. And that's for every M0 and M1. Right, so that's the essential attacker task. The whole attacker's goal is it M0 or is it M1 that is encrypted in the ciphertext I see? And what if basically we say, well, if he has this type of distinction advantage in saying, well, I think it's M0 and being correct, or I think it's M1 and being correct, versus I think it's M1, yeah, in the wrong case, if he does have an advantage. So in the correct cases, he does say slightly more often than in the incorrect cases, but that slightly more often is really slight. That's what we will want to say, and here's how we do so. So we need a notion of negligible probability or tiny in the phrasing above probability. negligible, or this doesn't have to be probability per se, it's just of negligible values or quantities. Okay, so I'm going to call a function that takes natural numbers and outputs whatever, real number. I'm going to call it negligible. If for every polynomial P, there exists a point such that for every point after there is a threshold point such that for every point after that one, the value of the function is upper bounded by 1 in polynomial of n. What does this mean? So intuitively, values of f are eventually upper bounded, so they're smaller than 1 over Pn for any polynomial P. Let me give you an example of a function that satisfies it. This function, 1 in 2 to the n, is negligible. Why is this? Okay. So to say it's negligible is to say, so let's check. Is it true that for every polynomial, so is it true that 1 over 2 to the n is eventually upper bounded by 1 over Pn for any polynomial P? Well, that holds even only if I put this here and I put this here. If Pn is upper bounded by 2 to the n. And that's just right. I just multiply both sides by Pn and I multiply both sides by 2 to the n. This is something that you are very well acquainted with. You know that for every polynomial P, there is a point such that for every n greater than n0, this is true. Right? This is the whole notion of difference between polynomial time computation and exponential, right? No matter how big polynomial you have, eventually, so for n large enough, an exponential takes over and is larger than the polynomial. And that's what it means by eventually. There is a point that such that for every value after that point, this equation is true. And this is even only if. So exactly the same thing is true after I put this in the denominator and I put this in the denominator, right? So there is really no difference between these two statements. This is the one that you know very well. And this is the one I'm introducing by saying that this function is negligible. All the statement says after moving this here is the statement that you already know very well. Okay. Also, like this function, say n over 2. So say that the brute force attack, it takes twice smaller keys. It doesn't need to guess n bits. It's enough as half the bits, and it already works. And therefore, a random choice of this half the bits has this probability of succeeding. Well, that's also negligible because this is true even only if I move this up and I move this up. the polynomial is eventually upper bounded by 2 to the n over 2. And now this is another statement that is exactly, that is also true in this sense, right? That for every polynomial, there is a value of n, some threshold value, I call it n0, such that for all larger, this thing is greater than the value of the polynomial, right? In fact, these two are the same statement, so you just scale the polynomial appropriately, and this implies that. It's just you rename the polynomial. And I can give many other such examples. Basically, every example of a function that is faster than a polynomial, just divide it. Just don't think of the function itself, but 1 over that one. And now it's going to be upper bounded by 1 over any polynomial. But functions like f of n equal to 1 of n to the d for any constant d, in other words, 1 in some polynomial, are not negligible. Right? And why? Why not? Because 1 over n to the d is actually larger, strictly larger than 1 n to the d plus 1. So, and this thing is a polynomial. So here is an example of a polynomial that violates this, right? That polynomial, 1 over that polynomial does not upper bound this function. In fact, this function is larger than 1 over that polynomial. Just take one more degree and, right? So 1 over n squared is not exponential because it's not bounded above by, for example, 1 over n cubed. And 1 over n cubed is not negligible because it's, it's not bounded by above by, for example, 1 over n to the 4th, right, etc. So this is and by the way, this function, polynomial over an exponential, is also a negligible function. And this will be like a homework exercise. If you have a negligible function like this one, and you multiply it polynomially many times, did you move from a negligible function to a non-negligible one? And no, you have not. Okay, and that's a good thing to verify. If you have a bunch of negligible functions and you add them together, do you get still negligible or not? This is important for us because if we say that basically everything that happens with a tiny or negligible probability we disregard, then we need to know like what happens. Okay, what if that tiny thing happens with polynomially many times? Because let's say I have a crypto system where I pick polynomially many keys and I do something with them. Each of them, by the assumption about the cryptographic building block, has a negligible chance of failing, of being attacked. But I have polynomially many of them. So exactly I have a case like this, where I had a negligible function and I multiplied it polynomially many times. I need to note that this is still negligible. Okay, so that's an exercise, and I guess here is so given this notion of what's negligible, basically I will just finish by actually saying this. So here is the computational notion of encryption security. I'm just taking both of the constraints that I was talking about today. It says for every efficient, meaning polynomial time, attacker algorithms A, and for every messages M0, M1 in the message space, the probability that this attacker, and I'm going to just think of the single possible output is a bit, and I'm just going to measure the probability that this bit is equal to 1, because the probability that is equal to 0 is just 1 minus that. So the probability that 1 is output by the attacker, who is fed as input an encryption of M0. And this goes over the random keys and randomness of E and A. And if I compare this to the probability that A outputs the same judgment 1, meaning A thinks that M1 is encrypted, given actually an encryption of M1. So this is a judgment, that is correct. And that one also goes over a random key and the randomness of encryption algorithm and of the attacker algorithm. So if I compare these and just simply see, is there a difference between them? How big the difference is? This has to be smaller than negligible amount. And mind you, negligibility is stated as a function. Notice that what's negligible is not any particular value. What's negligible is a function. So this is a negligible function of let's say key length. Okay, so this is something that we'll call security parameter. Later on, but it's more intuitive. Think, okay, there is an encryption. There is the keys are random bit strings of some length, and I just want this advantage to be negligible in that length. Because that means that if I just increase this length, I will attain the bound that suits me. No matter what this negligible function is, it's for quite small n, it will be as low as I could possibly want it to be. Okay, so this will be, for example, this attack, which was a counterexample of the notion, basically this more primitive notion, asks that these two are the same, and therefore this difference between them is simply 0. And now we relax, we say it's okay if the difference is tiny, meaning negligible. And what was the difference here? Well, the one of them was 0, the other one over 2 to the n. So the difference, and I take universal value, is 1 into 2 to the n, which is my flagship example of a negligible function, right? The first example of a negligible function. And if I grow to here, the difference between them would be upper bounded by this, and that would be the homework exercise. But I will not reveal a huge secret by saying this is still a negligible function, no matter how big this polynomial is. Okay. Okay. sorry for going a little longer. Is there questions on this? I'll switch off recording.